Good afternoon, everyone. I am Michelle Petrie, and this is the Sterling Engine Group B industry presentation number 2. We are one of the two groups who did the hardware packaging system for the Sterling Engine project that students are to do in their second semester at SAIT. This presentation will be about 10 minutes, and it'll be presented by myself, Michelle Petrie, alongside Joel Ajen, Kevin Nguyen, and Santino Saraceni. So for our agenda, we're going to be going over quickly the client request, so sort of our problem statement, our scope. Then we're going to be going over our preferred solution, our bowl designs that fit in with our preferred solution, our bearing solution, the purchase parts that we utilize to really help us out with this project, and different challenges that we ended up facing throughout our time working on this. So to start, just a quick recap of what it is we were really trying to do. So our goal was to put together baggies like this right here in an automated fashion that would be small enough to fit into a RoboCell, be able to put together 200 of those bags in about approximately 6 hours, not damage the parts, and be able to count it without any issues of putting in too many parts or too little, anything like that, making sure that it's accurate. And I'm going to be passing it on to Santino.
So our preferred solution to this was a hybrid system. So rather than going fully robotic or fully individual feeders, we kind of found the common ground, and we realized that using a robot to handle the bearings and then individual feeders for all the rest of the screws and nuts and everything was the ideal solution. So for the next slide. So for the bowl design, here we have a little GIF. If it loads on your side, it's kind of slow here. But essentially that's just the 3D printing of a bowl. And in these following slides, I'll explain to you how we designed that bowl. Next slide, please. So the first thing we had to address was the type of hole we wanted to use for it. And as a screw has to successfully drop through, our idea was to only have one screw at a time. So we started off by using a profile of the screw, as you can see in the top two pictures on the left of the screen. And while this did work, it had some issues. So then we moved to a rectangular sized hole profile. And then that worked much better, except it often allowed two screws to fall through at once, depending how they are orientated. And ultimately, our final solution for the screws and the washers was a circular hole, as you can see in the left, kind of in the center of the screen, close to the bottom. And how we tested those different ideas was just with inserts that we placed into our essentially a spinning platform. And then for the phenolic spacers, they're long and cylindrical, so they wouldn't fall into a hole quite as nicely because they were so tall. So they did end up working best as a rectangular hole, as you can see in the picture on the left. Next slide. Then we had to determine the size of the bowl. And as you can see on the left here, the size varies quite drastically between the different bowls. And that's mainly to do with how many parts or how many of each part is needed per packaging. So in the biggest bowl there, we needed 20 screws per bag. And then in these smaller bowls, we only needed 1 or maybe 2. And how we determine the size, we use this, as you can see, the diagram closer to the bottom here. So we essentially took the diameter of the screw heads and just calculated a cylindrical volume, and then ensured that our bowl, the inner volume of the bowl, was at least 1.5 times the amount of volume of the screws would take up. And for the washers, very similar, but obviously a bit more simple because they already are a cylinder. Next slide. And then we also have to determine how to mount them. And so we wanted to keep it as simple as we could as we were having to build this. So we figured we would use a slot to hold the motor from turning. and then the bowl would attach directly to the motor drive shaft. And the slot would go all the way through the boards, and that way it would also act as the drop-through hole. It was very simple to make, but we did come across a problem with the smaller bowls, and you can kind of see our solution in the the left picture. The top 4 motors, they're actually flipped around because if they were the other way, the screws would be dropping right onto the motor and not successfully make it out of the system. So we flipped the motors around and then added a separate drop-through hole, and that solved that problem there.
So come to bearings. Bearing is one of our biggest challenges because bearing was shipped to us in plastic bag, which cannot be used the normal way to sort it out like auto washer or bunk. So after researching and finalizing, we suggest 2 solutions. The first one would be the magnet, and the second one would be the vacuum generator. Next slide, please. So for the magnet solutions, due to the magnetic properties of bearings, using magnetic to move bearings is a possible solution that should be considered. In this solution, we use magnet to move in an inclined motions, which we're taking one by one, follow the inclined path and fall into the conveyor. The downside of this solution is it requires a certain type of magnet, like it's not too strong but not too weak, because if it's too strong, it takes more than one bearings at a time, and then if it's too weak, it cannot bring the bearings up to like the point that we need. The second solution would be the vacuum generator. So we're planning on using robot ABB IRB 140 in the robot lab. The 2 changers and the adapter are required for attaching the vacuum generator into the robot. But for these solutions, the bearings have to be stacked up so that it can provide like a certain surface area for the vacuum generator to pick it up one by one. And the downside of this solution would be programming, because that's one of the hardest things. So next slide, please. As you can see here, we have like the SolidWorks photo right here. You can see the robot ABB IRB 140 and the tool changer for both robot side and the tool side, and an adapter which is 3D printed, and of course a Festool vacuum generator. So at the picture below here, those are like the 3D printed prototype for the adapters. So I'm gonna pass you John to talk about the purchase part.
So I'm gonna quickly go over the parts that were not provided by the lab. Obviously, with our project in mind, we had to go out and buy some parts. I'm not sure, can you see me? I think so. Anyway, so I'm gonna talk about the motors that we sourced. So on the next slide. The motors that we used are really low gear ratio motors to make a nice smooth movement for the parts to fall in the holes. The motors that are used here are fairly cheap, with $7 per motor, very affordable, very compact. They also have a built-in mechanism which saves the gears from if there's any kind of blockage, that the gears won't damage, so like a ratchet mechanism. Next, I'm going to talk about the sensors that we sourced. These are IR beam breakers, IR beam sensors, fairly easy to use. They use a light barrier. If that light barrier is broken, it brings a signal to our PLC. Very cheap too, $4 per piece, very affordable. Then next, I'm going to talk about the wires. Servo wires have been used for our project. The male end had to be cut off and was soldered onto a breadboard, which I'm going to talk about on the next slide, the breadboard here. For the breadboard, the reason we use the breadboard is the sensors that we used use 3 to 6 volts. And unfortunately, the PLC uses 24 volts, so we had to keep that in mind and sort that out. So what we used is transistors and resistors to adjust the signal to 24 volts for our PLC. We used the breadboard to connect all that together to make it nice and compact and easy to troubleshoot later on. Thank you.
Apologies. Of course, now we're going to go over the challenges that we experienced throughout the project. So a lot of these challenges were also experienced by the other teams, but they were different blocks that ended up either making us have to rethink what we were doing or causing different issues for us. And we felt it was important to mention these just because it's important to know the kind of things that can affect a group like this throughout the course of the project. So first off, time. Time is the big one. I think everybody had issues with time, whether it was time available on campus, being that for most of the semester, we were only really allowed to be on campus for 3 hours a week to work on our projects. And of course, we understand COVID is an issue, and so we understand that the COVID-based restrictions on time was something that everybody experienced, but it definitely set things back, that's for sure. And then otherwise, time for our prints and printer calibration. So a lot of our parts, mainly, well, the bowls, were 3D printed for this. And so if we had a print fail, whether it was just something happened with the filament or it wasn't properly calibrated, which it happens. It's frustrating, but it happens. It would mean having to reprint them to make sure that things were as efficient as possible. And that really ended up eating some time, especially because our bowls could go from being printed in approximately an hour to having to be printed in 2 to 3 days. So that was definitely a concern. Our next one is the filled bowl weight. So as mentioned before, one of the parts, we need to have 20 of them in each bag. So that's one of our screws. And when we ended up trying to figure out approximately how much that would weigh, it ended up being a lot heavier than we thought at 4 kilograms. And so that's pretty hefty. And we really needed to reevaluate if our bowl was going to be strong enough and if our structure was going to be strong enough for that. And then, of course, alongside that is the size reevaluation of the bowls. So with figuring out the weights and with figuring out the volumes, that meant figuring out new bowl sizes. And so as mentioned before, we wanted to make sure that they were at least 1.5 times the size of the volume that all of the parts were going to fit in. So we had to make sure that it was different sizes to hold everything. And new sizes, of course, meant more prints and, once again, more time. So in conclusion, we decided that the best method to do this would be a hybrid system utilizing the ABB IRB 140 robots for the bearings, and then our own system with bowl feeders for all of the other parts. The bowl feeders were based on the size and shape of the hardware, both in how much they could hold and also the holes that we ended up using for being able to distribute them. The bearings, we decided to use them for the IRB 140 with the vacuum gripper that we showed earlier for that, which we found using a vacuum for that was a lot more efficient and a lot better for what we needed. And of course, our main challenges, with the biggest one being time. To finish this off before we head on to our questions, we just really wanted to say thank you to everyone for being here. We especially want to say thank you to our instructors for this semester and for our course over our time at SAIT, and our clients. So a big thank you to Dan, Chris, Joan, and Aman. And are there any questions?
Yeah, I have one, Michelle. How many cycles did you test any of these bowls to? How many times did you run them? How many passes did you put through a bowl? I'd like to get an idea of how effective it was with those little motors.
I think Santino would be able to better answer that question.
When it came down to actually testing the final bowl design, we only got probably in total about 3 minutes. Actually, no, I'm sure it's closer to 10 minutes of actual testing. Just because with the time we were focused on building the structure and everything. but we were able to test it. So yeah, you saw that video before. That was part of our testing. Yeah, we probably ran it for about 10 minutes, successfully totally emptied the bowl several times, but we weren't able to fill it up to the capacity that would usually be filled up for the 200 bags worth. But it should work no problem with that amount of screws as well.
Actually, no, I understand why you didn't fill it. We didn't give you enough parts to fill it.
That was part of it.
That would have been rather cost prohibitive for us to do that. Yes, but okay, thank you.
All right. Any other questions?
Doesn't look like it. Thank you very much, team. Good project. Good presentation.
Thank you.
Thank
Thank
you.
everyone for joining.